It's
Yeah.
actually like the set of all things
Yeah.
that give you this property.
Let me.
In V, not the dual.
Right.
For all operators.
Let me foolishly try a concrete example here. This may go horribly, terribly wrong, but let me try. All right. So I'll try to make it as small as I possibly can and not make it just entirely, I mean, I can't go one-dimensional, but let's try 2. Let's try, I think it's B2, I'll keep it real, right? So we're talking about, matrices of the form what? Like B, excuse me, M11, M12, M220, right? These kind of matrices, upper triangular matrices. I believe, and we'll look at these. We'll identify this as a subset of GL2R, okay? And more specifically, let me say it this way, GLR2. There we go. That's the notation. So my V is R2. Okay? Are we good so far?
Yeah, that's VNR.
Yeah, V is R2. So in this case, we could figure out what the eigenspaces are, right? I mean, we can figure out that there's going to be like a V lambda 1, which is the span of E1, right? And we can figure out there's going to be V lambda 2, which is the span of E2. I mean, I think that's just apparent that those are the common eigenvectors of all of the matrices of this type, right?
Yeah.
I think, unless I'm missing something, unless I'm being too naive about this. Hopefully I'm not.
You can't get more than 2 eigenvalues.
Well, yeah. So I'm kind of trying to work backwards. If these are the weight spaces, what are the weights, right? What's lambda? Lambda 1 of what we have. Lambda 1 has to define it. Lambda 1 on what? On M, right? What's lambda 2 on M? In fact, let me be even a little bit lazier still. Let me be a little bit lazier than this, Audric. Let me make this the diagonal 2 by 2 matrices. Let me put this M12 to 0, just to hedge my bets here a bit, okay? Is that okay? Let me do that. Then I'm definitely sure that your weights are, this is M11, this is M22. That's the formula for it, right? I believe. Oh. I've learned something, Audric. I've learned something. It's a dual to the operator space, not a dual to V. So what I'm saying is, D2R, it's the span of like E11, E12, right? So if I call this thing beta, the dual basis to that, I would typically denote E1 upper 11, that's 22, my bad. E upper 22, 22. Sorry, I'm an idiot. And so like generically speaking, if I was to say Eij times EKL, you could talk about the dual basis to the matrix units, if you were so inclined. And so these are particular examples of these duals to the matrix units. In particular, like lambda 1 of m. I said it's m11, right? But you could just as well write that e11 acting on the m. Lambda 2m, it's m22, sure enough. But you could write that as e22 acting on the m, which is to say, I have two weights. Lambda 1 is e11. Lambda 2 is e22. So, and I don't think that I have any freedom to scale or multiply these or even add them. Like, I think that those are the weights. I think that's it. There's just those two. I can't, like, the set of weights are these two things, I believe. Now, I could be wrong. Maybe there's more. Maybe there's more. I bet there's more. Can you guys tell me another eigenvector of diagonal 2 by 2 matrix, which is diagonal? Oh, yeah, there's more. There's more. This is just, there's more. My bad, there's more. If M is a diagonal matrix, tell me what equation this is true for. Oh! Oh, I was thinking that I could do this mv is equal to some constant times. Oh, I can't say that. I can't say that it's just some constant times v again, generally speaking, because when the m multiplies the v, it multiplies different parts of the v differently. So only if I have, I need the, I either need m to, if m is equal to the identity, well, great, then that works for any v, right? So yeah, it's true that I could put iv equals to v for arbitrary v. That's what I was thinking about. But that's not terribly important or relevant to this discussion, because what we're trying to do is find eigenvectors across the totality of the algebra, right? So the fact that this one has, like a larger class of eigenvectors, I'm looking for common eigenvectors across the whole of the algebra, which is a more complicated problem, right? I think the most rudimentary example of the problem we're grappling with is seen in linear algebra when you're trying to simultaneously diagonalize two operators. You guys may or may not know this, but this is the theorem. If you want to simultaneously diagonalize t and s, if and only if what? What's a sufficient, what condition do you need on two operators on a vector space for there to be a basis which simultaneously diagonalizes both? The condition that you need is that they commute.
Independence of the bases.
You need that they commute. Which of course we could understand as being that the commutator is 0, right? And I think this invariant lemma is replacing 0 with a what? Essentially, like A, the ideal, is playing the role of 0, right? Like things are getting sucked back into the ideal again.
Okay.
This whole thing is a play on this theorem. Like, It's unfortunately a theorem which I am scared to cover these days in linear algebra. Like it's right on the edge of what gets me into trouble. Like I once taught linear algebra, like I taught it well, and then I got to talk to the chairperson about why my course evaluations were so bad, and I was like, honestly, I've never tried harder at this course. And my reward was to have to come and talk about my teaching after the semester.
Well, I just submitted your course evaluations.
Oh, well, thank you. Okay, so listen, let me go on here. So chapter 6 is on Engel's and Lee's theorem. Let me state them for you. Listen, I will try to talk to my relative, my brother, and double check my intuition on these things. I'm sure there's something I'm not saying that should be said that, I will talk to Bill and try to figure out what it is I'm missing here. I will follow Bill's advice, though, and not prove Engel's and Lee's theorem. Bill's like, it's more important to show what comes afterwards and how these things like work together. And I guess I understand. I mean, the proof of these is fun. And anyway, so here it is, Engel's theorem. Let V be a vector space. L subalgebra, sub-Lie algebra of GLV. All right, such that every element of L is nilpotent transformation on V. All right. Then there exists basis of V in which every element of L is represented by a strictly upper triangular matrix. So Engel was a contemporary of even one of these 19th century dudes who came along, and I forget exactly. I don't know. They all did different parts. Some of them did more than others, but Engel's an important part of the story. So this is Engel's theorem. Let's see here. Another version, the second version, and the second version is proved with the first in this book, okay? So the second version is this. A Lie algebra L is nilpotent all right, if and only if for all x in L the linear map add x from L to L is nilpotent. In other words, a Lie algebra is nilpotent if and only if every adjoint operator on L is nilpotent. he says it's very tempting to assume the Lie algebra GLV is nilpotent if and only if there is a basis of V such that the elements of L are represented by strictly upper triangular matrices. However, the only if direction is false. Any one-dimensional Lie algebra is trivially nilpotent, and he gives another example here. Let's see here. Then we get the Lie's theorem. All right. So what's Lie's theorem? Lie's theorem says the following: let V be n-dimensional complex vector space. All right, and let L be solvable. Lie subalgebra of GLV. Then there exists a basis for V in which every element of L is represented by a upper triangular matrix. Do you see the difference? What's the difference? Yeah, solvable versus what? Nilpotent, right? And do you see the difference in the kind of matrices we're looking at? Right, exactly. So this is key difference, upper triangular versus strictly upper triangular. So if you want to come up with examples of Lie algebras, right, that are nilpotent, then strictly upper triangular matrices are a good bet. If you want to come up with examples of Lie algebras which are solvable, then upper triangular matrices are your bet. And in some sense, what Engel's theorem and Lie's theorem say is, up to a choice of notation, nilpotent Lie algebras are strictly upper triangular matrices. Up to a choice of notation, solvable Lie algebras are upper triangular matrices. And again, there's a warning about not overstating that statement in the chapter that I should go. Now, if I have time, and I hope I have time, I would like to go on because this is, you know, I'm pretty sure, Audric, we're going to come back to this concept of weight as we go on in here. Oh yeah, I'm supposed to go on for a bit longer here today, aren't I? Let's go on to the next chapter because that's where it starts to get interesting again. I mean, I think the thing we did last time, right, about what is a simple Lie algebra, you know, the simple versus semi-simple, the radical, all of that, that's, of course, very interesting. But so these things we're looking at, they are part of the story which builds to the theorem, which I just stated without proof last time, right? Like that any simple Lie algebra or semi-simple Lie algebra can be built as a direct sum of simple Lie algebras. And the simple Lie algebras look like they do. I think ultimately these things stem from the theoretical tidbits we're accumulating here. Okay, so some representation theory. This is chapter 7. And I think there are things to learn here that are, you know, beyond just what we're doing. What is representation theory is an important question for any student of pure mathematics. And there are a lot of different ways to understand that question. You see, there's group representation theory. All right, we can talk about, in group theory, we can talk about a group action. So if you have a set, you can let a group act on that set according to the axioms of a group action, right? And there's all kinds of interesting applications for that. Like, for example, you can study something called the class equation, and you can study how permutations act on themselves and things. I wouldn't say Galois theory yet, but what I'm talking about, this conversation leads to Celo's theorems. Like, Celo's theorems are naturally derived from looking at the group action, the question of what is the group action and how that all works out. So group representation theory then is something different still, though, because group representation would be something like you have a set of a matrix group, all right, and that matrix group is homomorphic to a given group that you have, and that homomorphic image of the matrix group acts on a vector space. That would be a group representation. So what we're talking about here is a representation of a Lie algebra. And so here's the definition. My point to you is that the term representation is not native to this topic alone. It's part of a larger theme in mathematics. I'm just showing you an example of representation theory. What a given person means by representation theory might be different. When a physicist talks about representation theory, your guess is as good as mine. Let L be, they mean all of it. Okay? They mean any part of the representation theory that they need to write the equations that they care about. And if it's a mixture of group representations and algebra representations, so be it. Right? What's a spinor? You know, a spinor is a particular representation of something called the spin group, I believe. It's a representation of the double cover of the Lorentz group or something like that. Man, I'd like to give a talk about that in here. That would be awesome. Let's see here. I think we're running out of semester, though. Let L be a Lie algebra over a field F. Okay? A representation of L is a Lie algebra homomorphism phi, where does it go? It goes from L to GLV, right, where V is finite dimensional vector space over F. Right? And he says for brevity, we'll sometimes omit mention of the homomorphism and just say that V is a representation of L. All right. Now, of course, you can also trade out the linear transformation for the matrix and talk about a matrix representation, right? So he says sometimes it's called a matrix representation, right? Was it a question, Audric?
No.
Have I gotten ahead of your reading?
Yes, you have. Or my notes, yes, you've got.
Ha ha!
You won't cover the 2 chapters, right? No first we give it Oh, that space and left.
All right, so let's see here. So here's some examples. The adjoint map. Add, it's mapping from L to GLL. All right. How is this defined? Of course, it's defined as the adjoint on x acting on y is given by the bracket of x and y, like that. Remember, we had that the kernel of the adjoint the adjoint mapping is actually equal to the center of the Lie algebra, right? So if you want the homomorphism to be, so you can talk about the representation being faithful. What would it mean for it to be faithful? So like the kernel of phi is trivial, all right? And I guess then it would be a faithful representation of L onto its image in GLV, if that was the case. You'd have a one-to-one bijection. So if it's faithful, then you have a Lie algebra isomorphism into the set of transformations or matrices of your representing space. So over here, the adjoint mapping is faithful if the center of the Lie algebra is trivial, right? Yeah. So, and he says, hence the adjoint representation is faithful precisely when the center of L is 0. For example, this happens when we're looking at SL2C. So the center of SL2C is equal to 0. Now let's work exercise 7.1. All right, let's do this one. It's a good one for us to do. Let's work out the adjoint representation of SL2. So I should try to use the standard notation. What was the standard notation? I don't remember. We're talking about, I'm going to go back to using A for the matrix, if that's okay. A such that the trace of A is equal to 0. I think that was it, right? That was the special linear, just traceless, right? So, I think he has the notation here. Let me steal. Where was it? Exercise. Oh, the basis exercise 1.12. I got to look back. 1.12 is where he. There it is. Woohoo! That's what I've been looking for. E is equal to 0, 1, 0, 0. F is equal to 0, 0, 1, 0. And H is 1, 0, 0, minus 1. I wish I could remember. Oh yeah? Can you tell me what are the brackets going on here? What you got? E.
It's like.
What's E with F? What's?
EF is like. I think one of them is just straight up H. The other one is 2E. The other one is minus 2F.
So what's E with? Let's see. E with F. E with H. What's F with H? Oh, these are in the homework I haven't graded, huh?
Yeah.
My apologies. You should demand a refund.
Here it is.
This is actually an important example. We can learn very, very much from studying SL2C.
FH is 2F. HF is FH is 2F. HE is equal to 2E, and EF is equal to H.
So I put a minus because I got EH.
Yeah, because it's their anti-commutative, yeah.
I think that's enough. I can get everything from those. Okay? So if I want to find the adjoint representation, right? I'm gonna use basis I'm going to let my basis be what's going to go first. Probably, I sure hope it's E and then F and then H. Otherwise, that's really annoying. So let's assume that that's the correct order. The alphabet order of the basis is the correct one. Please let it be so.
It's HEF.
What? Are you kidding me? You better be kidding me.
No.
Oh, he does do HEF. Son of a... All right, fine. I'll do it. All right, so to find the matrix representation of that, to find the matrix representation of the adjoint representation rather of SL2, what I want to do is I want to look at what is like add H, right? Of H, add H of E, add H of F. What are those equal to? 0, right? The H with E, the H with F, what do those work out to? Well, H with E apparently is 2E. H with F apparently is minus 2F. All right? So, yeah?
Well, the adjoint operator would put that one in the first slot, so you have to flip the minus signs now.
What you talking about?
By our construction of the mapping, it would be H and E, and EH is minus 2E. Oh, you already flipped it from dummy.
Oh, okay, good. Okay, so from this, I can see that the matrix of the adjoint of H with respect to this basis, all right, is equal to, well, 0, all right, and then my second column, I got 2E, which is 0, 2, 0, and then I got an F, which is 0, 0, minus 2. So that's the representation of the adjoint. Now if I do the adjoint, let's see here, what's the adjoint of E? Oh yeah, E, okay, E. What's that one look like?
We do the same thing, right?
Yeah, well again I got to do H first. So H with E gives me, so that's 0, so the first column I'm getting from, E with H, minus 2E, which is 0, minus 2, 0, I believe.
And then 2 with F, right?
And then E with E, so the second one's 0, because E with E is 0. The second column's the E column, right? The third one is E with F. E with F is H, which is 1, 0, 0, I think. Like that.
Oh, E with H is minus 2E. Okay. 1, 0, 0. Okay, I'm with you.
And then if we calculate the representation adjoint of F, yeah, again using our unalphabetically appealing incorrect HEF basis choice. I'm gonna have to talk to my brother about this. What's that?
2F.
Oh, I do H first, right? FH gives me what? Oh, 2F, which is 0, 0, 2 is what that looks like, right?
0.
And then you said F with H. Oh, 2F?
Minus H.
Wait a minute.
No, sorry, F with H is 2F. F with E is minus H.
F with E, oh, minus H, which is minus 1, 0, 0, right? And then, oh, the last one, 0,
Zeros.
right? Well, he has add H given in 7.1. That was nice of him, wasn't it? So here I'm claiming that that's the other two, all right? I mean, the adjoint in some sense is very, it's ridiculously greedy. I mean, you're going from a 3 by 3, like from a 3-dimensional thing to essentially like a 9-dimensional space, right? Because like these 3 by 3 matrices. I don't know. It's the adjoint's always a funny thing to me. But there it is. Then his example 2 here, he's got the inclusion map from L to GLV is trivially algebra home. What's he saying here? Suppose L is a subalgebra of GLV. I think what he's saying in example 2 is that if L is already a subalgebra of GLV, it's its own representation by the identity map on itself, which is an exceedingly silly example, but there it is. All right. He said, we've seen several such representations, mostly in the form of matrices, SLNC, or the upper triangular matrices BNC. The Lie algebras considered in exercise 3.3 all have natural representations. The natural representation is always faithful. Oh, okay. So like if we were to look at this idea, for example, with like B, B2R or something like that, then I'm not saying we'd look at the adjoint for that. I'm saying if we were to look at this, then it is a representation of B2R. So like the point is it's already a matrix, right? It's a representation. Let's see, Lie algebra, homomorphism. I mean, you can talk about just the inclusion map from B2R into GLR2, and that's the Lie algebra homomorphism, and it's faithful because the kernel of this is, I mean, it's a one-to-one map. It's just the identity map restricted to here, so it's going to be a bijection onto its image at least. So yeah. Interesting. So chapter, I mean, there's more to cover in chapter 7, and we will cover more in chapter 7. Let me see how my time is going.
It's 5 o'clock for you.
5 o'clock for me. It's 5 o'clock somewhere. Oh, I guess it is. It's an example of the inclusion that I was just talking about. Yeah. But chapter 8 is on representations of SL2C. And I think there is where it starts to get. I'm trying to find the weights coming back to us, right? I know there's like this. Man, I can't remember where it comes up. It's. I'm trying to come full circle here, you know? Let's see here. Okay, I think it's chapter 10 that the weights come back, Audric. We have this thing called the root space decomposition. And so, yeah, we'll get back to the weights when we get to chapter 10, basically. You see, and here's the punchline in the introduction. We may therefore decompose L into a direct sum of weight spaces for the adjoint action of H. Our strategy, therefore, is to find an abelian Lie subalgebra H of L that consists entirely of semisimple elements, and to decompose L into weight spaces for the action of the adjoint H, and then to exploit this decomposition to determine information about the structure constants of L. So that's the game plan for chapter 10. So that leads to this something called the Cartan subalgebra, and there's this root space decomposition. Then he gets these root strings of eigenvalues, and oh, you actually get an inner product of all things in that. So there's like a natural sort of Euclidean geometry of all this stuff. And then ultimately you start building these pictures like you see in chapter 11 of these root systems. And then that gives rise to these Dinkin diagrams, which give you sort of a diagrammatic way of tracing out the possibilities, which is then put into practice in chapter 12, where the Dinkin diagrams, different ways you can draw them, are used to explain why there are these 5 families of the simple algebras that we talked about last class. So that's the big scheme of things, but you know, we're here at the moment, right? Okay, so let me go on here. I don't know. I enjoy calculating the adjoint. I don't know what it's just fun. But let's see here. So corresponding to a representation, you can talk about a a module. And so let's do that here. So definition. Come on. So this is modules for Lie algebras. So here's the definition for that. Suppose L is a Lie algebra over a field F. All right. A Lie module for L, or an L module, if you like, is a finite dimensional F vector space. All right. V together with a map. It's a map. It's a map. It's a map. It's a map. I have to be careful about that. It's become a loaded phrase. L cross V goes to V. Dora the Explorer has become very dark recently. L cross V maps to V. Audric's like, no, Dr. Cook, no. Stop that. I don't know what you're talking about. It's very good. Audric is not engaging. He's wise. Let's see here. So x dot v, oh, satisfying. Module axiom 1, m1, lambda x plus mu y dot v is equal to lambda x dot v plus mu y dot v. Module axiom 2, m2, x dot lambda v plus mu w is equal to lambda x dot v plus mu x dot w. Some parentheses as appropriate over here. And oh, finally, something. I'm like, where's the Lie algebras in any of this, you know? Here it is. So the Lie bracket of x and y dotted with v is equal to, ooh, look at that, x dot y dot v. So it resembles the commutator, but with dots. Why? How much do you bet the commutator is an example of one of these? The for all x and y in L and v and w in v and lambda and mu in F. So this is a Lie module. He says, for example, if V is a vector space, L is a Lie subalgebra of GLV, then one can readily verify that V is an L module, where x dot V is the image of V under the linear map X. This is axioms M1 and M2 are equivalent to saying that the map X comma V maps to XV is bilinear, right? And condition M2 implies for each X and L, the map V. Let me write this. So M2, it's saying that for each X and L, V maps to X dot V is linear. Endomorphism of V. That's just a fancy way of saying a linear map from V to V, right? Endomorphism. So elements of L act on V by linear maps. The significance of M3 will be revealed shortly. All right. He says Lie modules and representations are two different ways to describe the same structures. If you're given a homomorphism, you can make a module and vice versa. All right, so like, you give me a module, I can give you a homomorphism. If I give you a homomorphism, you ought to be able to make a module. What's the interplay? So let's see here, it's pretty much inescapable if you start with one and try to get the other. So let's assume we have a representation, right? Suppose, start here. All right? Now I want to define x comma v maps to x dot v. How should I define that? Using my handy dandy Lie algebra homomorphism. What should I do? What do I need? So x is where?
So you're a homomorphism?
Yeah, I have this to play with.
I mean, all you need is, like, a homomorphism is just, you can, you know, like, phi.
Yeah, I gotta use,
That's the definition of a homomorphism.
I mean, I need to use phi. What can I feed to phi? I need to put something in from L into phi, right? So what do I have to put here?
X.
Yeah, I have to put x. Now that is what? Phi of x is what? Phi of x is an element.
GLV.
Yeah, phi of x is an element of GLV. So what do you do with that? Well, the only thing you can do, you let it act on V, right? That's the only thing I got to work with here, so let that, if you like parentheses like I do, act on V. They probably don't write the parentheses. And, well, at least it's the right kind of thing, right? It's supposed to be is it an element of V? Sure is, right? So I'm taking in a pair, x comma V, outputting an element of V. Now we got to run through the axioms. So like, for example, lambda x plus mu y dot V would be equal to what? Phi, right, phi of lambda x plus mu y acting on V, right? And like you said, because this is a homomorphism, we can pull the lambda out, and
Phi of x acting on V plus mu, was that y of phi of y acting on V?
right,
Ergo, yeah.
right. So
Times V plus mu y times V.
so yeah, it follows immediately from the linearity of the homomorphism, and then module axiom 2 follows from the fact that phi of the thing, phi of whatever you input, is in GLV. So module 2 is coming from the fact that the image of the homomorphism is in linear maps. That's where you get module 2 axiom from. Module 3 is perhaps interesting. Module 3, if I had to wager, is probably going to be like, I mean, somewhere the Jacobi identity has to pop up in here. Like a day is not, we have not talked about the Jacobi identity yet today. Like I feel I have not done my job until we've done the Jacobi identity somewhere. Stupid girls. I can be working on the other board right now, not for the, I mean, women. Whatever. Anyway, them and their nonsense hall meeting thing over there. So annoying. Okay, I think we'll be back to 2 boards again next class, Audric. It seems to be a Monday. You like the 1 board? Oh, that's right. Ah, I forget. You don't like to. I forget you don't like to be. It's an odd thing for a runner not to like to be moved. But anyway. Okay, so how about this one? Let's try this out. xy dot v would be phi of the bracket of x and y, right, acting on v. But this is, how does that go? It's a Lie algebra homomorphism, right? So this is supposed to be like phi of x comma phi of y acting on v. But this is the commutator. It's the bracket in GLV. Right? So phi is a homomorphism from where? From L to GLV, right? So just to recap what's going on here, I actually made it. I actually made it that time, Audric. No one's here to see it, but so here you got your abstract bracket. All right? And over here, we're talking about, you take 2 operators, t and s. You're looking at t composed with s minus s composed with t. That's the bracket in the linear transformations. So when I put that into practice over here, I'm looking at phi of x of phi of y of v minus phi of y of phi of x of v, which is also known as phi of x, and this would give me y dot v minus phi of y, and that would give you your x dot v. But then applying the definition once more, I will run out of space. annoyingly, and have to write it right over where I'm trying to get to, which is super annoying. So I'm going to have to erase my previous comment. Sorry, Audric, you got this part?
I didn't get that.
Oh.
No, I got it.
Oh, okay. So this is straight up x dot parentheses y dot v minus y dot parentheses x dot v, which of course is that. So, oh man, no Jacobi. No Jacobi. That's lame. Come on, Jacobi, come back to us. No Jacobi. So sad. So up next here, we have submodules and factor modules. A submodule of V is a subspace W of V, which is invariant under the action of L. In other words, for each x and L and each w and w, we have x dot w as an element of W. In the language of representation, submodules are known as subrepresentations. All right. This seems like a very good place for us to start next time. So I'm gonna stop right here. I don't want to. These are like larger linear algebra ideas that I want to make sure we don't hurry through. So I'll try to start right here next time. I think that's a good spot for us to kind of lay anchor. Do you guys have any questions about stuff we did today?
Yeah, I'm gonna have to look up the what were we talking about, like the dual space, invariance, weight.
Oh, yeah. I'll try to double check with Bill and make sure I'm not. Yeah, I'm selling you guys a bill of goods. You know, bill of goods. Sure, he's never heard that before.
I'll make sure to do my course evaluations after teach another class.